Advanced Financial Modeling, Topic 7, Option Valuation and Hedging, Learning Objective number 3. We're going to compute and understand implied vols, vol term structure, and strike skew. So we're going to calculate something called implied volatility. What implied volatility? It is the standard deviation input to Black-Scholes, which will result in the Black-Scholes price being equal to the market price. So when I inserted the Black-Scholes model using a volatility of 30%, it gave me a market price of a model price of $16. If, however, the actual market price of that call is 10.05, what we could find out is, well, what standard deviation would cause the Black-Scholes price to go to 10.05, and the same for the put. So that's the concept of Black-Scholes implied volatilities. What we're going to do is we're going to run it using GoalSeek. So we'll go to our spreadsheet, and we could run a GoalSeek, and I'll do a data, what if, GoalSeek, set the Black-Scholes price to 10.05, that's the market price, by changing the input to Black-Scholes, hit OK. And I get 18.67. So I'll just type that in there, 18.67. And I can do the same thing with the put, data, what if, GoalSeek, set the put price to a value of 11.05 by changing vol, hit OK. It says 1921, I'll hit cancel and type in 19.21. So that's one way of getting Black-Scholes implieds. And what the idea behind this is, well, if I truly believed in my estimate of 30% volatility, this call is selling for $10. I think it should be worth $16. So what you think is maybe I should buy the call because it's an underlying, or you should sell the call. Rewind it again. Since the call is selling for $10 and I think it's $16, I think I should buy it. If the put is selling for $11, I value it at $17. I think I should buy it because both the call and put seem to be undervalued. However, volatility is really hard to estimate. So what you might also think is, well, maybe I don't really know what the volatility is. And if the traders are using this Black-Scholes model and they're smart enough to come up with the market prices, or the market prices are determined by all these traders' actions, maybe I'm not as smart as I think I am. Maybe the true volatility is closer to 18 or 19%, and these are fairly priced options. So that's the concept of implied vol. It's also been shown that these implied volatilities are good estimates of future volatility for other purposes. So that's the concept of implied vol. Now what I want to show you is a program, VBA program for puts and for calls that calculate implied vol that doesn't require you to run GoalSeek. And what's interesting about these programs is they use a different type of looping structure. It's the only different looping structure I'm going to give you in the course. And we've always used for loops, for I equal 1 to n next I. However, I'm going to do a do while loop. So do while loop. This is the loop. Everything in the middle is going to get repeated. So here's the function. It's called put vol. You put in the underlying spot price, the strike price, the interest rate, the maturity of the option, the dividend yield, and the market price of the option. However, this program also assumes you have BS call and BS put inside your same module, so it's going to use that. So here's how the model works. The model says that the model starts off by saying, well, the highest possible vol is 1, in other words, 100%, and the lowest possible vol is 0%. So it starts off with high vol and low vol. That's defined as kind of the minimum and maximum implied volatility. And this says, do while the difference between high and low vol is greater than 0.01. Well, right now, the difference between high and low vol is 1 minus 0. And here's where all the action happens. If BS put, so what's this going to do? This is actually going to value the option using BS put. So this is going to call up the BS put program, wherever that BS put program is. It has the same parameters. It's going to get the spot price from here, the vol from here, the average. The vol is the average of high and low vol. So initially that's set to the average of 100 and 0. It's going to be 50%. So it's going to value the option using 50%. It's the average of high and low. And then it picks up the interest rate T and D from our parameters of the option. So it's going to value the put using 50% vol if that put price is greater than the market price. So if the Black-Scholes put is giving me too high a valuation, then I'm going to lower the high vol, and I'm going to set the high vol equal to the average of high and low. So I'm going to set the high vol to 50%. So it's going to get reset. High vol is going to now be 50%. It's then going to, if that's too high, it's going to send it back up and now revalue the option using the average of 50 and 0, which is 25%. Now remember, our actual implied vol is about 19. So it's still going to find that it's going to be too high. So what it's going to do, it's going to reset high vol to be the average of the 50 and 0. So it's going to set high vol to 25%. Now it's going to revalue the put using 0 and 25. It's actually going to use 12.5. However, at that point, it's going to be too low, and it's going to raise the low vol. So here's what it's doing. It's setting the high vol and the low vol to 100% and 0%. It's using the BS put function to figure out that if when valuing the option using this, it's too high, it's going to reset high vol to a lower value, 50. And if it's too high again, it's going to reset it to 25. And if that's too low, then it's going to raise this one to the average of 25 and 0 or 12.5. So it's going to zero in on a vol by keep valuing the option and comparing it to the market price. So that's kind of an ingenious type program. And the do while says keep doing this until the difference between high and low vol converge. So that is the put vol function. Call vol is exactly the same, except it's using BS call. So let's go ahead and insert those programs. You can see it's a lot easier than running goal seek all the time, especially if things change. Notice 1867 and 1921. I'm going to put in my function, call vol, put in the spot price of the asset, 614, strike price, 615, interest rate, 0.1, T, 0.05, dividend yield, 0. Keep going down, market price, 1005, and hit OK. There's my 1867. I'm going to highlight all of that, hit F4, copy the function, and change this to put vol. Except for the put vol, I need to make the asset price 1105. So I'll slide that down, and there's my 1867 and 1921. So that's a program, 2 programs to calculate call implied vol and put implied vol. So how are implied vols used? One is it's often used as a price quote. So on this particular option, you might want to communicate that this option here, this call, is selling for 10.05, or this put is selling for 11.05. But that's almost never what's communicated to you. If you ask a trader, what are you selling the a March 615 call? They'll say it's selling at 1867 vol, and the put's selling at 1921 vol. So they're actually quoting you the implied volatility from the Black-Scholes model. So it's often a quoting mechanism for options. And let's just understand why that's actually kind of useful. Well, because this underlying stock price is changing every minute. So it's nice to be able to get a quote and say, I'm willing to buy, the person on the other side of the phone says, I'm willing to sell you this call option at 1867 vol. So when this changes to 615 and 610 and 605, 605 and 650, you have an idea of where that trader is willing to buy and sell. All right, so that's useful. Also, the implied volatilities are used as volatility estimates for things like portfolio optimization, like we did in topic 1 and 2. That implied volatilities are also used to add value at risk parameters. So if I need to know what the standard deviation of Google is to calculate the value at risk of holding Google stock, I would probably first look at an implied volatility. They often use the implied volatility of one option with an observable price to calculate the price of another option of the same asset. So if you're trying to figure out where should this 625 strike call sell for, and there's no price yet, well, just calculate the implied volatility of a 615 in which it does have a price, and then use that to value the option. It's also used as a test of Black-Scholes. So the implied volatilities are used as a test of Black-Scholes. So according to the Black-Scholes model, sometimes called the Black-Scholes-Merton model, because that's another person who worked on this model, the underlying asset returns are constant, or volatility is constant. We call that homoscedasticity. Therefore, the implied volatilities for all the options and all the strikes of that asset should be the same. If you calculate in different implied volatilities for different strikes and different maturities, that's a strike against the Black-Scholes model. The assumption of known and constant volatility is violated. So let's talk more about this implied volatility. And a couple of things we like to often graph implied volatilities in two different situations and kind of think about that. So let's first talk about, what if I were to start graphing the implied volatilities, say for a particular put, and using, say, the 615 strike, and then use other strikes, say 630, 640, 610, 605. And then just graph the implied volatilities. According to Black-Scholes, that should be a straight line, because you're talking about the volatility of the underlying asset, not the volatility of the actual option. In practice, however, you wind up with a different implied volatility for different strikes. In this case, if you got an implied volatility higher for the out of the money and in the money put strike than the lower one, if I connected these with a graph, first of all, I'll call this the strike skew, or the implied volatility structure. And if it's graphed like this, where the out of the money and in the money strikes are greater than the at the money strike, we call that a Vols smile, because it kind of looks like a smile, right? There's a face, there's a nose. So sometimes when we graph them, we get implied volatilities that look like this, kind of even on the right side and really high for the out of the money put strike. And we call that a smirk, like a crooked smile. So why does this happen? I'll give you a clue. Smiles and smirks really started to appear after the 1987 stock market crash. In that day, the stock market fell about 19 standard deviations, which should happen only about once in every many billions of years. However, drops like that have happened before too. Earlier in the century, it happened during the Great Depression. There were moves like that. So when that 1987 stock crash hit, and the Black-Scholes model was developed shortly before that, people weren't really questioning the assumption of normal distribution. But when that stock market crash happened, you would say that you would calculate there's really no chance of such a large change in the market, so I'm going to not value options that much. They're really out of the money. However, when you see a bunch of crashes like that, you start thinking, well, you know what? I don't think that normal distributions really describe the distribution of stock returns. I think every once in a while, those big changes happen more than what a 19 standard deviation would imply as far as a probability from a normal curve. However, Black-Scholes is the standard model. So what do? Well, you price the option and come up with some price using normal, the standard deviation you input. And then you say, you know what, I'll pay more for that option because I think the chance of that price going way down is a lot more than what a normal distribution would imply. So you kind of bid up the price of these out of the money strikes However, everyone's still using Black-Scholes. So how do you communicate you want to pay more for that option? Well, you just say the implied volatility is higher. So that's why we wind up with smiles. Why Smirks? Well, you just think that price drops are more likely than price increases. All right, so there's the strike skew for Google in 2019. These are for different maturities, and we see a smirk, we see a smirk, we see a smirk, we see a kind of a crooked smile smirk. So this is very persistent, and it's reflecting that Black-Scholes, the assumption of Black-Scholes of normality, normal distributions of returns, is clearly violated in the marketplace or in data, and therefore I'll just bid up the price of those out-of-money puts, or the probability that the stock price could fall. Sometimes we also like to graph the implied volatilities of different strikes. Okay? I'm sorry, different maturities. This was different strikes. But what if I just do 615 strike, but do, say, a 1-year option, a 2-year option, and a 3-year option? And we graph it. Well, according to Black-Scholes, it should be a straight line. Practice is it's not. It's usually upward sloping, downward sloping, or kind of a straight line. So why is this happening? Because we found that there is some autoregression in volatility. In other words, if a stock is having a very volatile period, say standard deviations are 35% or so. However, the long-term average is, say, 20%. We see that volatility tends to go back to long-term average. So if I'm pricing a 1-year option or a 1-week option versus a 3-year option, I would probably use closer to what it's been running to price the short-dated option and closer to what the long-term average is. So again, this is another violation of Black-Scholes' assumption of a constant known volatility. When you see a downward sloping term structure of volatility, it implies that volatility is high and it's above its long-term average. If you see an upward sloping, it says volatility is low, below its long-term average. Here's July 2019, some term structure or time skew of volatility for Google, and you can see it's got a kind of a kink in it and then goes long. It kind of does a long-term upward sloping. So last slide in this section. Strike skew is due to the trader's belief that stock returns are not normally distributed as BSM, Black-Scholes, Merton implies. Time skew violates the BSM assumption of homoscedasticity, constant volatility. However, everyone still uses Black-Scholes, at least to value and to quote option prices. So that leads to two views of Black and Scholes. I'll say one view is Black and Scholes were sent by God to show us how the real world works, and they gave us a model that's perfect and good. The second view is that these people are really false gods, demigods. That no one really believes this model. No one believes normal distributions on stock returns. However, it is kind of a handy way of communicating prices, so we'll just use it even though no one actually believes it. So at some point, you need to figure out your view. Are Black and Scholes gods, or are they just useful idiots that allow us to quote the prices of options using implied volatility? In the next sections, we're going to talk about estimating volatility, and we're going to revisit EWMA volatility, and then start moving into GARCH, and then we'll talk about simulating option hedging strategies.